Okay, Laplace domain analysis is not trivial. There's a lot of algebra involved. It is relatively easy to make an algebraic mistake along the way. One of the things you can do to verify your results is to actually do a simulation. So here I'm going to show you how to do an Ltspice simulation of the two example problems that we worked previously. So here's the first example, problem 4.4-4 from the text. If you remember, it had the two inductors and the voltage source that's changed from 3 to 6. I'm only interested in the voltage for t greater than 0, so I'm going to set my voltage source equal to 6. Something to note here that may be a little different from your use of a Ltspice in the past, that I specify the initial conditions here on my inductor currents as being 2 amps and 1 amp, and this is how I do that I can edit the actual value of inductance, and then after the inductance value include the initial condition IC is equal to 2 amps, and for an inductor that will be the initial inductor current. The other thing that's really important is you want to make sure that you've got the current direction for the inductor correct. Depending on how you insert it, in this case with the inductor laid out horizontally, the assumed Ltspice assumed inductor current might be either to the left or to the right. In my circuit, it was the initial current was assumed going to the right, so I need to check that. So I can do that after the simulation. Bring in a current probe to verify that the current is flowing from left to right as shown here, or if I hover over the second inductor, I see that the assumed inductor current is also flowing from left to right. That's important. If the assumed inductor current is flowing in the wrong direction, is in the other direction, then my initial current would be wrong and I won't get the right solution. The other thing is going to do a transient simulation here over 5 seconds. That's enough time for these transient components to die out. But the other thing that we need to do is in the simulation, you also want to skip this, check this skip initial operating point solution. That will include this UIC term in the simulation command. That UIC means use initial conditions, and we want to actually use initial conditions here, so you have to check that box to include the initial conditions. Now run the simulation. It produces, in this case, what I have in the top plot is I've plotted the current through the first inductor, and then in the bottom plot I'm showing the plot of the current through the second inductor. I've also, in each of these plots, you can, by right-clicking and say add a trace, what I've done is actually add my theoretical expressions here. Again, when you enter this in Ltspice, the syntax is a little tricky. You have to enter in the actual variable time, not t. And then also notice I've included some units here, so that this is actually in amps, and if I don't do that, it may actually plot them on a different scale. I'll show that here. You'll see here now I've got two separate curves, and it's actually plotting this expression using this right hand axis, which uses a different scale. It goes from 2 to 4. Where my inductor current is plotted over here, and it goes from 0 to 4. So in order to get them to use just the same axis for comparison, I need to make sure that this is actually in the right units. So I'm going to include amps everywhere, and now I see just the one axis, and this allows me to directly compare the simulated current with the theoretical expression that we derived earlier. And do a similar thing for the second inductor current, and plot it, and then also plot the theoretical expression. Here they overlap. I mean, they almost completely overlap. And I I can show a little bit of difference maybe by just multiplying this by 1.1 to plot to show a little bit of separation there between, so that you can see that there really are two curves. If I remove that term, we see that they almost completely overlap. So this gives me a lot of confidence that I've got the right theoretical expression. Similarly for the second circuit, which involved a capacitor, again, you have to make sure that the correct polarity is across the capacitor. Again, you can do that with a current probe here showing left to right, which would correspond to a assumed positive polarity on the left. The IC here in this case actually specifies the initial voltage across the capacitor, and then again also in this simulation command we need to make sure that we've got this skip initial operating point solution checked, so that the simulation actually uses the initial conditions. So this was the second problem. We're interested in actually the current through the capacitor, so that's what I plot here along with the theoretical expression that we derived, and so again they overlap. So again, I'm fairly confident in my theoretical solution. Let me just give you a few Ltspice simulation tips if you want to verify your own results. And specify the initial capacitor voltage and voltages and inductor currents using the IC equal value notation, okay, after the component value. You can also, I didn't in these simulations, but we do have the University of Evansville Ltspice library that has dotted components. Makes it a little easier to determine the assumed current direction and or assumed voltage polarity. Okay. So use either the dotted components or check the assumed component current direction. You have to do that after simulation, and then if it's incorrect, just flip the component around. Okay. And then we need to run a transient analysis with initial conditions. So that's with UIC. And so to get that, you have to check that skip initial operating point solution. Another tip is in the waveform viewer, include units with your expression of volts or amps. So 1.5 amps times exp minus 4 times time, for example. Or another example would be 10 volts times cosine of 2 times pi. Ltspice knows the pi variable. You spell it out, pi times 100 times time. By default, in Ltspice in the waveform viewer, the trigonometric functions require their argument to be in degrees. So I'll throw in the conversion factor of 180 over pi to get my argument actually in degrees, so it'll plot the right thing. So that's something that you want to remember. I'll put that down as a tip. In the waveform viewer, where you're plotting these expressions, waveform viewer, trig functions take their argument in degrees. Trig functions are in degrees. Okay. And a final tip that actually I didn't use it in this simulation, but because the sources I used were actually, in this case, they were both just DC sources. You can get much more complex voltage and or current sources by using what are known as the behavioral voltage, and that corresponding component is a BV component, or current, BI source, for kind of arbitrary input currents, input voltages or currents. So, for example, I can include a voltage that's time, that's t e to the minus 3t. I could write that in using a behavior voltage source. It's time times exp minus 3 times time times cosine of 4 times pi times time, for example. Okay. Kind of a quirk of Ltspice is that for the behavioral voltage or current sources, the trigonometric functions expect the argument to be in radians, so I don't have to include the conversion factor here. So again, it's just something that you'll need to get used to. I'll provide a handout in class with all of these tips nicely typed out for you, so you can use it for reference as you do your own Ltspice simulations.